Today, we're going to end up doing some stuff with a special subclass of tensors, right? So tensors are the following thing. Actually, let's do this. Oftentimes, you'll work with some kind of vector space. Okay? So V is a generic vector space of some kind, and the most typical that you might work with is like the real numbers or something. Right? So what makes this a vector space? Okay. Well, you need to be able to add things. Right? So what I mean by that is you get a set, and you should be able to add things. You should have somewhere where you get scalars from. So you should have some kind of scalar field, like real numbers. Okay? And then you should be able to multiply the real numbers with elements of the vector space. So an example, of course, is you let A be an element of the real numbers. So that's a scalar. You let V be in your vector space, just some arbitrary vector. I know engineers sometimes will write a little thing like this. I used to do this, but it gets so tedious, and it makes your markup, if you're writing LaTeX or something, look really ugly after a while, especially with the kind of Einstein tensor notation for indices that we're going to use later. So I just avoid it. Sometimes you'll see people write vectors in bold, excuse me. That's another common thing. I think Landau does that in his books.
What's the latex?
It's so for bold, it's math BF.
Okay.
And then you put like curly braces V. If you wanted the vector, little arrow above.
The vec.
Yeah, vec V. And yeah, many times you just don't do anything. Hello. Hello. So we're just recovering what a vector space is. Right? So namely, you have a set. You can add things together in the set, whatever that means. I can tell you, I can add this monitor up with that tablet right there. And that would give you a vector space if you have the other properties. Who cares what it means to actually add the things? I just say we can add them, and then we get something called sums of the vectors. And then you have a scalar field for any vector space. You should be able to scale stuff. And you have an operation for doing so. So you take an element of the scalar field, you take an element of the vector space, and you should be able to form something like this. And you get that this is an element of the vector space. Okay? Whatever that means. You also have the property that, let's see, you should be able to do stuff like this. Right. So you should be able to like factor stuff out, and there should be some nice distributive properties for the scalar multiplication. I mean, there's a list of axioms I can list out, but you should have an intuitive sense. I can add things which are vectors, and I can multiply them by scalars. Oftentimes, not with our stuff, but if you're ever working in physics, almost all the vector fields you work, or vector spaces you work with, are going to be complex. So you're not going to have real numbers for your scalars, but instead you'll have complex numbers. It could go very far into that. Like in Galois theory, fields happen to be vector spaces over other fields, so the complex numbers are a vector space over the real numbers, and that they have a dimension of 2. Right? The rational numbers are a field. If you want to think of the real numbers as a vector space, with rationals being your scalars, the dimension of that is going to be infinity. Uncountably infinite. But in general, for any vector space, you have something else associated with it called a covector space. So let V be a vector space, and we'll assume this whole time that they're real. So the scalars are real numbers. Then we define this. V star, the dual space, to be the set of of all the functions. So we should say f mapping from V to R linear. Okay. So we call these things code vectors. And my claim is that, let's look at some examples. So look at R2 is B. And give me a vector in R2.
2, 3.
Okay. So that should look something like this. 1, 2, 1, 2, 3 should be here. Okay. You might also write it this way. So formally it's this, that's a two-tuple because it's coming from the Cartesian product of the real numbers with itself. But oftentimes I'll write things in a vector space as being column vectors like this. What that means is it's a linear combination of the basis vectors, namely 1, 0, and 0, 1, here and here. And sometimes I'll write this is E1, and this is E2. And so that just means that this is equal to 2E1 plus 3E2. This notation works anywhere. This is only valid for Cartesian products. Okay. Now, what might be, give me an example of a function f that is in, so I want f to be in the covector space. I want it to be a covector. How should I define f? So it's going to eat elements of R2. So it should take, let's take x and y as the coordinates. And how should I define this?
Sum of square of x and y.
Sum of squares?
X square plus y square.
You say like this is not linear, right?
Oh, that. 2x plus 3.
Okay. That's one example. And you can check if this is linear. How much do you do that? Well, what does it mean to be linear? It means that if you, this marker's a little bit dead. If you take a vector, if you take linear combinations, they should distribute over f. They should commute with f. So you've put f, this is completely dead. Let's see. You put f of x in 4 times the try. This is GSU standard.
Yeah. I need to cut this out from the video.
I'm glad there's at least markers, because half the time in the whiteboards at like the library, there's nothing.
Yeah. Yeah, my advisor always gives me a ton of them. Okay, this one's good. So we mostly avoid this issue. I like chalk because you can see when you're out.
Yeah.
Not markers. They should have like a bar where you can see how much ink is left in there or something.
That'd be really cool. Like a little window.
Yeah, like batteries used to have, you know, where you put your thumb on it and it would tell you how much juice you got left.
I didn't know they did that.
There's a lot, like early 2000s, maybe the last time I saw one.
That's cool. I didn't know that.
Yeah, I mean, what you do to check that f is linear is you say, okay, f is not eating 2 different vectors. It's eating one vector, v. Okay, and that v lives in R2. So what I should be able to do is I should be able to say, okay, let's take a linear combination of 2 vectors. A u plus bv. And I should be able to check, does this get satisfied for any choice of a scalar, being a real number, u being a vector in R2, v being a vector in R2, and b being another scalar real number. This should be true. It should distribute. Okay. If I can check that, then I know that f is linear. If it turns out not to be true, then it's not linear. So this is the general method you use. And this tells you that it's linear for arbitrary linear combinations of vectors, not just 2, because linear combinations are finite weighted sums. You take finitely many pluses, and you can just do this over and over as many times as you need. process will repeat. So let's actually check it. So f, the general way of doing this is going to be taking a arbitrary. I'm going to write ux here, uy here for the components, plus b, vx, vy. This is just so I don't have to come up with new names for things. I'm just writing u with an index of x. And of course, this is going to be just writing this out as x and y, like over there, a two-tuple, two real numbers. I get, let's do it the simple way, a ux plus b vx, a uy plus b vy. And of course, this is just the same thing as having written a ux plus b vx, comma, a uy plus b vy. And I can now take that and stick it into the formula that Vern gave me. So that ends up being 2 times the first one plus 3 times the second one. 2a ux plus 2b vx plus 3 auy plus 3b vy. Now, this looks really ugly, but I just want to get it in this form. So I'm sure you guys have probably seen doing this before, especially if you've taken linear algebra. But it is necessary to see it. Like, for when we go up to tensor products, something like this will happen. We'll be doing things like this, but not exactly the same. So what I want to get, I want to show that this is what that is. So A for me is still just A here. So I want to group my A's together and my B's together. So let's do that. I'm going to commute these two. These two, because I want to get my A's and B's in front. And I get A times, and I'm going to take this term and factor. It's going to be 2ux plus 3uy. And then I have my B's. Did I do that right? Yes. Plus B. And then it's 2vx plus 3vy. And of course you can see this is A times f of ux, uy, plus B times f vx, vy, which is A times f of u plus B times f of v, and you're done. So you checked it and you heard. Okay, so the general form for a linear function on R2 is going to be almost exactly like what Varun gave me, which is you're going to have components, x and y, and it's going to be ax plus by in general. Another way you might write this, and if you're engineer-minded, you're going to think of doing things this way, is this is one vector in R2, and so you can think of it as a column matrix, and it's going to look like this. So f should take a vector, and it should be equal to multiplying that vector times a matrix. Matrices describe general linear operations. Now what should be the size of that matrix? What should be the shape? Rows and columns. Just think f needs to be taking us from V to R. So f is from R2 to R1.
So the 2 rows, 1 column?
2 columns, 1 row.
Yeah, 2 columns. Yeah, it's backwards from the way you read the function signature.
Oh, okay.
Here's one. So if I have a general linear function, f from, let's say, R, let's do it this way. If I've got a matrix, and I'm doing right side multiplication, let's say I've got A times a vector, or even A times B. Let's say this has size m by n, and this has to have size n by something.
Yeah.
Let's say L or K or something like that.
And the
No.
result will be m times k.
Yes. So if this is a column vector, then it has n many rows and only one column. So it'll end up being like this. K is 1.
Oh, yeah. Oh, I remember this from linear.
So just for the purposes of recording, I guess, what you're doing is you're taking, okay, I've got a matrix that's n by n, and it's mapping me from an n vector to an m vector. So m by n describes a mapping from Rn to Rm, so it is backwards always. So mnemonic, it flips it. So in general, this is from R2 to R, and so necessarily it must be a 1 by 2 matrix, flipped backwards. So if it's a 1 by 2, that means it has 1 row and 2 columns. So let's write that over here. The general covector format is going to be like this. It's going to be A, B times X and Y. So covectors are row vectors, same thing. Transposing gives you a covector. So what that means is I can take any finite dimensional vector and I can transpose it and I get a covector. And I can take any covector that's of finite dimensions and I can go back and get a vector. And so these two vector spaces, it turns out, are isomorphic. Covectors are, of course, just vectors, right? Because I can add row vectors together, much like I add column vectors together. And I can multiply these by scalars. They work just like these, they're just transposed. So covectors form a vector space called the dual space to any vector space of finite dimension. You can have them of infinite dimension as well, but the vector and covector spaces are not isomorphic anymore in infinite dimensional vector spaces. Now, how do you visualize a covector? Because, Ruin, you told me that I should write this as an arrow, or you gave me the components and I wrote it as an arrow. So how should I draw a covector? Namely, if I have 2, 3, if I have a vector 2, 3, and I find its dual, sometimes you'll see people say, okay, I've got a vector v, I want to find its dual. There's something called the dual map, which takes you from a vector to a covector and back. This is just called the dual map. It does not depend on the basis, because all it does is transposes. You get the same thing no matter what basis you chose for your vector space. So how should I draw? If this is 1, 2, 3, then I want to draw the dual to it, which is going to be 2, 3 as a row vector. And you might think I should just draw another arrow that looks the same way. But that's not the most natural way to draw it. I think it was in Richard Feynman's quantum electrodynamics book that I saw this, but the best way to draw it is a covector stack. So what that is the following. So let's say you had a unit vector, just this one, 1, 0, and you want to take the dual of it. So that's equal to 1, 0 as a row vector. How should you draw that? If it's a unit vector, it's very nice. What you do is you say, okay, at the origin, draw a line normal to the vector, and at the head of the vector, draw another line normal to it. And then at the same distance, keep going in each direction. So go to 2, 1, or 2, 0, and draw a line like that, still normal to the vector, like this. Like this. Okay. Now, I'm going to draw another vector. Namely, I'm going to draw, let's say, v equals 2 and 50. to draw an airplane. So you can imagine this cuts off and keeps going up for a long way. And I'm going to draw something to this effect. And it'll keep coming up here, and it'll reach right here at 50. It's very easy to see what the value of, so let's call this U star. U star is a function that eats a vector, it spits out a real number. It's very easy to see what it should be. It's going to be, as a matrix calculation, it's going to be this way. And if you do this matrix multiplication, you end up getting just 2. But notice that in the picture, the vector goes through the covector stacks twice. It goes through 2 of them. This seems like the kind of natural way to draw this. And it works in general. Now, I have the property that the vector is unit vector. What happens if it's not a unit vector anymore? Because that'll probably change the results you get when you do the calculations. So what about for this one? You say, okay, start at the origin, draw a normal line. And notice that I went 1 away in the direction of the vector to get the next covector underneath. Well, instead of going the same length as the vector, which is like 4 plus 9, so 13, right? Square root of 13 is the length of this. Go 1 over the square root of 13 away. And so by the time you have reached 1 distance away, you're going to have drawn square root of 13 many of these leaves. And just tile the whole plane with it. And now you can just draw vectors and you can figure out what the value of the covector on them is, just by looking at how many they pass through. So that one looks like 1, 2, 1, 2, and 3/4 maybe. So now you can evaluate pictorially what the values of these covectors are. All right. So I think before the other people show up, we have a couple minutes. So I can talk about tensors for a brief moment. I think some of those people know this stuff. If I have a vector space V, and I form something called the Cartesian product of V with itself, what do its elements look like? So I take U and little b in big B, and then an element of this looks like this. Just a pair. That's an arbitrary element of V cross B. I'm going to define something slightly different, which looks very similar, called a V tensor product with V. Okay. And this will have similar elements to this. In fact, any element here can be written the same way here, with a slight modification, just choosing U and V again. Like this. And that's it. Okay. But there is a weird property about this space that says the following. Let's say I have a scalar, okay? And I write, instead of this, I had written A, so A is a real number. AU V. This is still in V cross V, but it's not equal to this necessarily, unless like U is 0 or A is 0, and V is 0. Okay. It's generally not true. However, this, A U tensor product V is the same thing always as U tensor product A V. All I'm doing is saying, okay, take pairs and just identify things that I can yoink the scalar out of and stick in the other set. Say they're equal if I can do that. You have one other property, which is the following. Take 3 vectors, U, V, W, in V, and if you can write, I really should be working with another vector space here, because you can take tensor products of things that are two different vector spaces, like V and V prime or something, two separate spaces. But the idea should be clear from what I'm doing here. You have the following property. U plus V is a vector in V. Okay. And you can tensor product it with W, which is another vector in V. And this happens to be equal to this. U tensor product W plus V tensor product W. Okay. And vice versa, you can do it with the right side. U tensor product V plus W equals U tensor product V plus U tensor product W. The addition is commutative, the multiplication is not, so I cannot say in general that U tensor product with V is equal to V tensor product U. In fact, I don't know any relationship between the two, unless one of them is 0. If you have anything tensor product with 0, then you can imagine that this is the 0 scalar times some V, and then you can pull this out. In fact, you could say this is even equal to U tensor product 0 times 0 V, and this is the same thing as yoinking this over to the other side and saying, okay, 0 U 0 V, which is the same thing as 0 vector tensor product 0 vector. So if it has 0 anywhere in it, it's killed. Now, tensors obey the following construction. We call this bilinearity. So it's linear in the first argument. Is a linear equivalence here because I can pull out the scalars. And in fact, we write this, you can actually say that U tensor product V is an element of the vector space of V tensor product V. So I'm saying that this is a vector space. And the scalars, the way they operate is you just take an element here and multiply it times the scalar. And it happens to be equal to these two things. Simple. Why do we care about tensors? Let's say you've got a function from a collection of vector spaces. So this is V1, V2, Vn. So it eats a bunch of vectors in an n tuple. So this looks like V1, V2, so on, through Vn. And this produces some kind of number. So this is f of V1 through Vn. And this lives in R. In fact, they can live anywhere, it doesn't matter. Some other set, or some vector space, I should say. So we'll say V0. If you have a function that's defined this way, and it happens to also be multilinear, you know kind of what that means. It means if I pick out any of these, and I say, okay, V1, let's say A times V1 plus B times V1 prime, so just two vectors in V1. This is a vector space. It might be totally different from this. This might be real numbers. This might be C to the 80, whatever, any vector space. They don't have to be the same, so this might be totally a separate kind of vector from these. But if this property is true for any index, so you say A, F, V1, V2 up through Vn, plus B, F, V1 prime, V2 up through Vn. And if I could have done it with V2 as well, or V3 or Vn or anything, then you say that this function is multilinear. Any such function obeys the following property. So, this is a theorem. guys if people want. I know in the differential geometry textbook by Shlomo Sternberg, this is one of the first exercises in the book. So the theorem is let V0, V1 up through Vn be vector spaces. Let f be a function mapping from f at v1 cross v2 cross all the way through vn over to v naught. And it has to be multilinear. If it has this property, then there exists a function f, or p, excuse me. Let's do a different notation. Let's do psi from, instead of having the Cartesian product here, take the tensor product through Vn, and it maps over to V naught as well, and it's linear. Because this is a vector space. You lose the notion of multilinearity if you're coming out of a tensor product, but you can check that if you work with this stuff a lot. So then there exists psi mapping from the tensor product to the codomain of the original function, linear, such that this diagram, you have this space, over to V naught, and this is f, right? And then you have this function, psi, and then you have the tensor product space. And then there's another map here called the projection map, which says, okay, take a vector here. It's parenthesis, an element of V1, comma, element of V2, and so on through Vn, parenthesis. Just send it to V1, tensor product, V2, tensor product, so on through Vn. You get an element of this. That's what this map does. Okay. So that this meets. Hello. Hi. Alright, so the idea when I say that this diagram commutes is that I can start anywhere in the diagram at any of these objects, any of these vector spaces, and I can pick out a particular element. And I can send it any direction I want in this graph, right, this diagram. And no matter which direction I send it, you know, if I start here and I go down here and then here, it's the same as if I started here and went here. Doesn't matter which direction I go, where I start, where I end, I get the same thing. As long as I start and end it in the same place. Okay. So this is the, what do you call this? I guess fundamental property of tensor products, tensors. So that's the whole point. It's that anytime you get a multilinear function, it factors through a tensor product. Examples of multilinear functions are the determinant from linear algebra. Right? So that's the main one. Everything really is just determinants. It's not anything else really. So that's it for this treatment of tensors, I guess. Later we'll probably do stuff where we do tensor calculus, especially if we're doing the applications to control theory. Knowing how to do Einstein notation is really important. It lets you do calculations very quickly. You can do things like take matrix derivatives very efficiently. I know in deriving the linear quadratic regulators, there is a derivative of a certain kind of matrix product that is kind of unnatural to derive unless you're familiar with tensor notation for matrix algebra. So likely we'll see that if we do applications in that area. But that's it for tensors. There's really nothing else to them. You can just add them together and like put scalars and like things are identified. It's like Cartesian products, but literally there's nothing more to it. people talk about a tensor is like something that transforms like a tensor, right? You hear this sometimes physicists will say or something. But it becomes natural to treat those things if you study Einstein notation for the indices.
Sorry, I missed the first part. So tensor is like a vector, right?
So yeah, you take vector spaces and you do this formal operation called the tensor product of them, which is like taking a Cartesian product and then taking a quotient in the algebra sense. No, actually in the linear algebra sense, right? I think it formally is quotient. I might be wrong about that, but you do some kind of quotient-like operation where you say, okay, you take this thing and say it's equal to this. If you have like two vectors and a scalar, this is equal to this thing. So you can just move around your scalars and you can distribute linearly the sums in particular elements or particular components. And that's how you get tensors. Okay, how does this come into what we were doing last time, right? So we were talking about manifolds, tensor bundles, or excuse me, tangent bundles. You have something like, okay, we have manifolds, and loosely speaking, you draw a manifold, say a two-manifold, like the surface, and you say, okay, pick a point. I can look at that point as having a plane tangent to it, called the tangent plane, the tangent space to that point. Right, so if this is P, this is two-manifold M, smooth two-manifold, then this turns out to be TPM, which is isomorphic as a vector space to R2 if we're working over a real manifold. Okay. Well, we have vector spaces. Maybe it seems natural to work with dual spaces of those vector spaces. So where we have vectors here, tangent vectors, we might think to work with tangent covectors. Okay. Those are called cotangent vectors as well. So you can move them, just like you can move the scalars around, you can move the co around in the tangent vectors. Naming ones. So yeah, the way you view a cotangent vector is, you take the tangent bundle over a manifold. So M is a manifold. Take the tangent bundle Tm, and you say, okay, what are the elements of Tm? Well, you pick out a particular point first, and then in the tangent space to that point, you pick out a vector. So this is just a collection of tangent vectors with a topology on it. So you have two in manifold, if you have an in manifold to start with for your base space. And you have tangent vectors. So let's define something called the cotangent bundle. And you just write it this way. So this forms covectors in, or I should say two tangent spaces along the tangent bundle. So remember what the tangent bundle is. You have the manifold. Every point, you have a fibre. That fibre is a vector space of the same dimension that the manifold is. And the sections of the tangent bundle, the smooth sections of it, are vector fields of the manifold. I said something slightly wrong last time, which was that for a sphere, the tangent bundle is isomorphic to, what was it? The sphere cross product with R2, which isn't true. There's some global properties, like twistedness, that tell you that this is not the case. They're not even homeomorphic. So they're certainly not bundle isomorphic. So the reason we know this is because the Harry-Bolton theorem is true, right? You should be able to say, okay, if this is what this is, then I should be able to pick every point of S2, and I should be able to pick a particular element of R2 smoothly, and that should just be a vector field on the sphere. But if I were able to do that, then I should be able to say, okay, take points in S2, namely P, and map them to elements of the tangent space at P. So this is going to be M, so S2, map to T. So I should say, like, pick a particular P. It's going to map you to an element of the tangent space at P. And I should be able to pick P, and this is R2, so I could take 1, 1, for example. And this is smooth in this space. This is a smooth vector field over, excuse me, it's a smooth section of this product bundle, and so that's a vector field. But this is not 0 anywhere in R2, and the Harry-Ball theorem says that you can't pick the vector field over the sphere that is not 0 everywhere, and it's still smooth. And so this tells you that this thing is not the same thing as the tangent bundle over the sphere. I don't know of a simpler proof of that. It's hard to visualize the global twisting of the tangent spaces as you go around the sphere. I tried doing this. I can't do it. Maybe some people can, but it's hard for me. And if you were able to do it, you would actually be able to prove pretty easily, I think, that the Harry-Ball theorem is true. So how do you build this cotangent bundle? You do the same thing as you did for the tangent bundle. You say, okay, I've got a base space, manifold. M, and you say, okay, this is going to be the base space of a fiber bundle. So now, if M is an n-manifold, then I would like to place fibers at every point. So this is going to be T star M, and the fibers are going to be this thing. They'll just be, so you have an n manifold, so it's going to be R n dual. Okay, so the dual space to Rn. So whereas your tangent spaces were Rn, your cotangent spaces are going to be Rn dual. It's nothing fancier than that. And then you just glue them in such a way that you get an isomorphic bundle to your tangent space, to your tangent bundle. And you have global twisting. But locally, it's going to look like, you take the patch of M, and you want to take the fibers over this patch. Each one of these is going to have a covector space, which is going to be isomorphic because you're in finite dimensions, to R2. And you just take these all separately, the disjoint union, and map them, and they're going to be isomorphic to this thing. So call this subset of M, call that U, an open set, small. The fibers over U are going to be isomorphic to, if you pick U small enough, it's going to be isomorphic to U cross, what do you say, R2. Sorry. So this is called a local trivialization. Some bundles have locally trivial. Locally trivial neighborhoods. They act like the product of sets on the base space with the fibers. The example of this typically is the cylinder, right? So the cylinder is a fiber bundle of even Mobius band. I didn't really talk about bundles enough last time. I think it was kind of sporadic. But if you take a Mobius band, this is not isomorphic or homeomorphic to a cylinder. Namely, it's not orientable. Right? So if I put a vector at every point and make sure that this vector field, this normal vector field, is not 0 anywhere, I'm not able to do that because as I go around this side, I'll still be on the outside, but then when you get to this twist, you end up on the inside, and then you keep going in some kind of path around until you get back to the same point on the manifold. And this vector that you associated with this point will be pointing the opposite direction of that one. So this is not orientable. But a cylinder clearly is, because you can pick a vector here, and then walk anywhere else, and you'll still be on the outside if you walk this thing around. These are not homeomorphic, they're not the same space. But locally, as bundles over S1, they are S1, look at all the fibers over it, so extend vertically. And then that's going to be homeomorphic to if I did the same thing here. I just take a point in the base space, I look at all the fibers, an open set of base space that's small enough, I look at all the fibers, so go vertically, and you just get these little rectangles. Locally they look the same, but if you consider the global properties, there's the twisting here. And in fact, the only the only R bundles over S1 are the cylinder and the Mobius strip. So in fact, if I took this and added another twist, it would get the cylinder back. You can use this, you can show this using the structure groups, which we might look at when we do the Ronco algebra a little bit after. All right, so what do we have for TM? We have fibers being, this is the tangent bundle over manifold. Fibers are tangent spaces. 2 points. What are these sections? So sometimes people use this notation of like, they say, or this nomenclature where they say, you look vertically and you get fibers. It's kind of intuitive, and then you look horizontally and you have sections, so you're taking slices in some sense. So the sections, you just say, okay, look at the manifold. Look at every point. There's a vector space there, tangent space. There's another one here. And if you're going horizontally, then what you're doing is you're walking around the manifold, and every point on the manifold, you're picking something in the fiber. And you have to do it smoothly, and you get a vector at every point. These sections of the tangent bundle are vector fields, generic vector fields. You can get any vector field this way. Use particle there. What about the cotangent bundle? You already saw what the fibers are. I'll just write up, down, for vertical fibers. These are cotangent spaces to a point, namely the dual space to these tangent spaces. Horizontally, the sections are called differential one forms.
I think I lost you somewhere. So, so here like TM fibers are tangent spaces to point means like, is it like a tangent plane to the manifold? Is it something like that?
What was, I missed the last part.
TM fibers, is it like a tangent to the manifold?
This is, this thing is the tangent bundle over manifold M. And this is just the cotangent bundle over M.
Okay.
It's just a disjoint union of taking, for a manifold, like a surface, it's two-dimensional, so you have R2, you take the Cartesian product of, I shouldn't say that. Yes, actually, you take M as a set. You have a manifold, M. Every point has associated to it another copy of R2,
Okay.
separately. You take the disjoint union of, I'm saying that wrong. Oh yeah, you do, I wrote it. So for the cotangent bundle, we end up with this definition. As a set, it ends up being the disjoint union over every P in M of the cotangent space at P. So it's a covector space, it acts like a vector space. Same thing for the tangent space. It's just a disjoint union of a bunch of copies of R2. And then you put a topology on it by noting, like, you look at the smooth atlas over the manifold, which we did last time. And you have to have some compatibility between the charts on the atlas and that gives you some kind of canonical notion of twisting over the manifold of the tangent spaces. So like for the Mobius band, the tangent spaces to the Mobius band will twist around 1/2 loop as you walk around. And when they come back, they'll have twisted 1/2 loop in some sense. And so the orientation is going to get flipped.
Okay.
If you walk around, you get something kind of like what's called holonomy later, which is like you get a linear map from the space to itself. If you take all the vectors in the space and you walk them around, like you take the tangent space and you walk around, you will get a linear map from the space to itself. And it'll have the determinant -1 if the curve is on some non-orientable part of the manifold. Yes. That's right. I was thinking of like connected sums of other things, but
So like, is this so sometimes like when you talk about the dimensions, you say like half dimensions. So is this the base for that half dimension stuff?
I don't know what you mean. Half dimension.
Like if you take the Mobius strip, you say like it's like 1.5 dimensions.
They're both 2-dimensional, but the Mobius strip is twisted,
Okay.
so it doesn't have a trivial bundle structure, I would say. Non-orientable. Okay. What are these differential one-part things? Because that's kind of what I want to get into. So whereas for the tangent bundle, we had the sections being vector fields. How do we write those, right? They're linear combinations of partial derivative operators. Okay. So an example over, let's say R2. So what I might write is a section over the tangent bundle over R2 is a generic vector field on R2. Okay. And I'm going to write that there's a particular element living in here. Maybe, actually I can describe all of them. F of xy, del x plus g of xy, del y. Okay. Make sense? Just a generic vector field on R2. If I have a coordinate system, I can do this nice thing. In fact, if I have a Riemannian or a pseudo-Riemannian metric, I can do this nice thing. By virtue of our coordinate system, we can leverage the coordinates to get a Riemannian metric locally. And you can take this map, musical flat, and it takes you from elements of Tm over to elements of T star m. So it takes you from tangent vectors to cotangent vectors. And you have the corresponding inverse sharp. So these are musical notation. This is called musical isomorphisms. Takes you from the cotangent bundle, cotangent vectors, to tangent vectors. And I'm just going to write what it is. I'm not going to spend time like trying to develop why it should be written this way or anything. But if I actually apply, I think this is in Tm, right? For a particular, let's do this. Over R2, you have maybe this. It's a particular tangent vector at a point. I need to specify particularly that it's at like 0, 0 or something to say it's in the tangent level. But the flat of this should be a covector. And I'll write it this way. I'm not going to write this restriction, it's kind of superfluous. That's how you write tangent vectors. And because you can do this at every point on you can go back and forth. You should be able to do it over the sections over M, over the tangent level. So you should be able to keep the coefficient functions. So if I take that f and g for my coefficient functions, let's just do this, f del x plus g del y, I should be able to flat this, and I should get something f dx plus g dy. These things, I'm just going to walk over the algebra, they eat tangent vectors. And they spit out real numbers. Because they're covectors. In the cotangent spaces. Give me a tangent vector. So, like, just 2 numbers. 5, 7.
5 and 7.
5, 7. So that's going to be written 5 del x plus 7 del y.
So wait, why did you, in this example, why did you take the locality away? 0, 0.
Oh, because I only defined it on the tangent bundle. I did not define it on sections of the tangent bundle, which are described by these coefficient functions being multiplied times the basis vectors for a particular tangent space. So these coefficient functions, if you see those in some kind of description of tangent vectors, that tells you that you're working over a section, a vector field, instead of a particular tangent vector somewhere. And elements of this are particular tangent vectors somewhere.
Okay.
So this is not in here.
Okay.
I defined this on here, and then I can leverage the nicety of that definition to pull it up to sections. And it just acts the same on every tangent space according to the coordinate system that you're choosing. It just works naturally, but it's a technical caveat. Yeah, so take this. I'm going to take a particular choice of differential form, differential one form. Namely, I'm going to take just dx, and we're going to see how it acts on this tangent vector. Differential forms are covectors. They are linear functions. Differential one forms, I should say. So what that means is I can pull out the coefficients and distribute over the basis for the vector space. dx, and then I have del y. Okay. The one forms, the basis one forms, I should say, dx and dy, eat the corresponding basis tangent vectors and spit out 1 or 0. This is 1, this is 0. Super nice definition. You just get 5, that's all you get. Notice what we did, we said, okay, we have a tangent vector, think of it as a column vector like this, and I took dx, which you might think of as being 1, 0, and of course this just spits out 5. So you can write them. You can also write them with the coefficient functions now, namely, if I had a differential form which was sine of x divided by y, dx minus x squared y dy, you might write this as a covector, like this, sine x over y, and then negative x squared y. Easy. And so you get like matrix algebraic ways of doing computations. Okay. Now, we got like 20 minutes left. I won't get through everything, but at least I want to give some sense of how to use these things. So, as we build up to Differential Topology, we need some way of, let's see, how should I say this? Let me just not explain. Just do it. I'm calling these things differential one forms. I should be able to differentiate them. I won't explain it more than that. You'll see after the fact when we use it why I'm doing it. We're building up a new theory of integration is what we're doing. Okay. Take a function, a smooth function, on some manifold with a coordinate system. Namely, let's use Rn. Let's do it this way. I'll just give computational examples. I want to define what D is doing. So I can plug anything into D. It's an operator. And it takes me from functions. So D takes me from smooth functions on a manifold that take you from the manifold to the real numbers. And it maps the smooth functions to differential one forms, which I write this way. Or you can write it as sections of the cotangent bundle if you want. So D, I'm calling the exterior derivative operator. Takes you from smooth functions to differential one forms. Okay? So let's take this for example. If you've taken ODEs, you might have seen something that looks exactly like this. And what you do is you look at every variable, x, y, and z, that appears, you differentiate with respect to it. So what's the derivative of this with respect to x?
yz dx plus.
Yes, that's right. So it's in physics called the total differential. xz dy plus xy dz. So this is a formal operation. I'm also going to make another notational choice. I'm going to call these smooth functions on a manifold differential zero forms on a manifold. So we have one forms, which eat tangent vectors. We have zero forms, which eat points, and they spit out our numbers. So D takes you from zero forms to one forms. You can see that this is a one form now. Let's put in a smooth function and I get a one form. Let's see. All right. These one forms are a vector space. So I can take, for example, dx, and I can take tensor products of the one forms of the one forms. So example might be something like this. Now elements of that might look like this. Let's say m is R3 or something. It should be plus sine xy dz maybe. That's an example of an element up here. If m is R3 or R4 or anything that has three variables. Yeah. And then we do this other quotienting operation. So whereas we took Cartesian products like this and made them into this nice thing, tensor products where we can yoink around the scalars, so we get some additional properties on the things we're producting together, multiplying together. We make a further adjustment to the tensor products, and we write instead this. Instead of a tensor product, I write this wedge thing. Okay. It has the following properties. It is associative. Just like tensor product. In fact, it is a kind of tensor product. It's a quotient over the tensor algebra technically, but it's fine. It's associative, it's distributive over sums, and it is anti-commutative over basis forms. So when I say basis forms, I mean that this is a basis one form, this is a basis one form, this is a basis one form. It's just things that are d some coordinate. So the idea is this: dx wedge dy is equal to the negative dy wedge dx. Makes sense. In the notes, I actually show why this is true and construct this constructively. Just take it as a fact. What if I write this? Can this be simplified? What happens when I commute this? Negative dx wedge dx. Okay. And if something is in a vector space, if something's equal to the negative of itself, zero. So anytime you wedge a one form with a one form, if it's the same thing both times, you get zero. This is called the exterior algebra of, not yet. Actually it is. It's the exterior algebra of one forms. Differential forms, actually. I can wedge more things together. I can have something like dx wedge dy, wedge dz. And you can see what happens if I commute things. You know, if I swap these, I get negative. If I do another swap so that I moved x over to here, I get a positive. So it ends up being dy dz, dx, so on. But one thing I haven't described is, yes?
Is there a coincidence that you can also write like the wedge product in terms of the determinant, and the determinant is like multilinear?
That's exactly this next thing, yes. So the one thing I didn't describe is how it operates on tangent vectors. And you need determinant formula to see how that works. Kind of, I mean, it's the nicest way to compute with it. All right. let's do a calculation. I'm going to take, let's work in R4. And I'm going to let there be a vector field. And let's make it sine, so I'm going to pick coordinates u, v, x, y. So this will be sine xy, d, so del x plus 2 del y minus x cubed u. I should have written these as u and v, so let me go ahead and do that. X cubed u del x plus del y. This is a generic vector field over R4. So it's a section of the tangent bundle over R4. And let's pick a differential, I should be careful. These are called differential 2 forms. These are differential 3 forms. You can make higher forms by, of course you write that this is an element of the differential 3 forms over M. So just some notation. Okay. Now, I want to take a differential form over this, and let's make another vector. So I shouldn't call this V, I should call this like, let's see, W maybe, and then another one, I don't know, let's do X and Y, capital X and capital Y. And let's just make this one nice. Del X minus del Y. Still a vector field, but it's constant in terms of the coordinates. And I want to take a differential 2 form now, namely dx wedge dy plus du wedge dv. And I want to see how to apply it. So I haven't said exactly how these work. These are functions, wedge products are functions of, say, 2 tangent vectors now. So if I have a differential 2 form, it eats 2 tangent vectors and spits out a real number. If I have a differential 3 form, it eats 3 tangent vectors, so on. So this is a 2 form. As you see, it's a linear combination of basis 2 forms. And I should be able to plug in x and y and get some kind of numerical result. Well, if I plug in vector fields, I get a function result, but it's fine. So this ends up being, well, the sum. So I can just individually evaluate these. Okay. Plus dx wedge dy, x and y. Now I'm going to switch to the matrix notation. So this is going to be du wedge dv. So I'll still write that. I'm not going to use a row vector. You can't really write 2 forms and higher as row vectors, but I can write x that way. So x is this, sine xy, 2 negative x cubed u, and 1. And then we put in y, which is 0, 0, 1, negative 1. And then we have dx wedge dy, which is, again, sine xy, 2, negative x cubed u, 1, and 0, 0, 1, negative 1. Okay. Now, what is this? Well, no, this is the uth component, this is the vth component, and then you have x and y at the bottom. You use this to pick out which ones you're going to evaluate. Okay. So you have u and v. You have to write them in order first. So you want to sort them in alphabetical order. Very important, otherwise you get negatives of what you're doing. But what you say is, okay, construct a matrix where the uth component, let's see, am I doing that right? Yes, so construct the matrix, and it's going to be 2 by 2 because we have a 2 form. Take the left vector, put it on the left column of the matrix, but only select the u and v rows, the first 2. And then do the same for this, but only select the u and v here. Okay. And calculate the determinant. Simple. This one's 0, so I'll just mark that out. But then we also have to add to this thing. And for that one, you have x and y, so you just pick these. and it's going to be negative x cubed u, 1, negative 1 down here, and then 1 here. And you calculate the determinant. That is going to be positive x cubed u minus 1. So that's just evaluated the differential form on a pair of tangent vectors. Let's see. And one more thing, because I know we're like running out of time a little bit. I was able to differentiate 0 forms to go to 1 forms. I would like to be able to differentiate 1 forms, 2 forms, so on, and go up to the next. So 1 form should go to 2 forms, not differentiate. So how does that work? Can someone describe to me a differential 1 form? Like give me a particular one. Over R3. So 3 variables x, y, z. Just give me an example, like a function. Maybe polynomial or something. I feel like we come up with something too simple. Just give me random functions.
X squared, x, y, z.
Like this. Okay, so that will be for dx. And then I'll add plus, because I'm doing a 1 form, so it can't have any wedges. Give me another function. And I'll write that this is alpha.
X, Y, 40.
Okay, I see. So, yeah. Plus, let's do this. Let's twist it a little bit. Just to mess it up a little bit. Yeah, so how do I differentiate this? This is a 1 form. So it lives here. Over R3. And I want to take d of alpha. And what I do is I say, okay, I'm just going to look at a particular vector field with only 1 basis component, or basis covector. And I'm going to differentiate that alone. And I'm just going to look at the component, the coefficient part, and I'm going to take the exterior derivative of that. So it's going to be this. And then you wedge with whatever basis forms are there. Okay. And then you distribute, you do the same to all of them, because I can distribute this d over the different sums, because d is a derivation, it's linear, it's nice. So let's do that. So you have dx y squared z wedge dy minus dx y z cubed dz, but I need to write a wedge, unless your last name is Hestenes, in which case you have fancy methods. You don't need to do that. Kevin, have you seen David Hestenes, like the geometric algebra stuff? Okay.
No.
It's like popular on Twitter and stuff nowadays. So. I don't like how he does things, but anyway, he has a more general method. Okay, so what does this come out to be? We know how to differentiate these now to get 1 forms. So this ends up being 2x, y, z, dx. Okay, makes sense? Just differentiate it with respect to x only. Now with respect to y, x squared z dy. Now with respect to z, x squared y dz. Wedge dx. Well, this wedge product is distributive, so I know that this is going to die. Because I have dx wedge dx. This one, we'll just do the calculation really fast. Y squared z dx plus 2xyz dy plus x y squared dz wedge dy. And then finally, I have minus, and that's going to be yz cubed dx plus x z cubed dy plus 3xyz squared dz wedge dz. This dies, and then you just distribute, and you get, I'll just start writing it, but I won't write the whole thing. X squared z dy wedge dx. Now I want to reverse this to get them in alphabetical order, and I'll have to negate to do that. So let's go ahead and do it. Okay. So that's the result of that calculation. And yeah, you just keep going. Distribute them to here, and so on. I want to do one last little tiny example before I quit. Let me go ahead and pull up my laptop, so I don't have to do exactly before. Which is the integration over R2. You might know when you go to polar coordinates, you get this weird R in there. Right? So you get R dr d theta, you don't just get dr d theta instead of dx dy. So I want to show why that happens. There's a way to show it with Jacobians, but it's very natural with differential forms. And by the way, you do the same thing for 2 forms and 3 forms and so on. You just take the coefficient part and you exterior differentiate it and wedge with the rest of whatever you already got. So it's nice. Well, let's let, let's see, x equal r cosine theta, y equal r sine theta, and then take dx wedge dy, which is the thing you're usually integrating a function with respect to. And I want to show that this is equal to r dr wedge d theta. It's very easy. Just write d, okay, x is equal to this, so I just write it in there. Wedge dr sine theta, okay, it's equal like this. Now I can just apply the exterior derivative. Get 2 variables, r and theta. So differentiate with respect to r first. You get just cosine theta, and then you have to write what you differentiate with respect to, which is r. Plus differentiate with respect to theta. I'm going to get negative sign, so I'm going to go ahead and write minus r sine theta d theta. Okay, that's it for this part. Now wedge, and you get nearly the same thing. You get sine theta dr plus r cosine theta d theta. Now you should distribute. Notice something. When you multiply this with this, it's going to go away because you have dr twice. Right? So we only have to do these and these. In FOIL, only f and l live. In this case. So what do we get? We get cosine times r times cosine, and you have dr wedge d theta in that order. So you get r cosine squared theta, dr wedge d theta, and then you have minus r sine theta times sine theta, so sine squared theta, and then you have d theta wedge dr. Now what should I do to simplify for me? Anti-commute. Collect. Factor out your r. I should go the other way. Cosine squared. That's 1. R dr wedge d theta. So this makes it very natural to do change of variables. You don't have to compute Jacobians anymore, even though it ends up being a lot of the same computation. But you also get later some nice geometrical interpretations of things. So this is really, really nice. Okay, that's all.
How do you go from one form that you use?
Forms?
From one form to 2 form?
You take.
Sorry, 2 form to 3 form.
Yes. Let me help him lecture real quick before I do that.
Sure. I just want to see an example like
Yes. I'll do just a basis. 2 form. Because linear combinations, you just do the same thing over and over. Let me go ahead and pull this up. Alright, so let's say you have like x squared y dx wedge dy. Let's do z, sorry. And this is dy. And I want to take the exterior derivative of this. you just apply this here, so you get rid of this parenthesis. And then you put a
Oh.
wedge, and that's all. It's very simple. Okay. Alright, so
Thank you.